Okay, now let's look at the problem 5.7.4. So in this problem, we have three reservoirs connected with the layout that I show in the figure here. And the elevation of the reservoir A is equal to 100 feet, and the elevation for the reservoir B is equal to 80 feet. That's weird. And the elevation for the reservoir C is equal to 120 feet. And the rest of the pipe characteristics are shown in this table. And the problem want to access what is the discharge in each pipe in this figure. Okay, so from the elevation information here, we can obviously see that we should pump the water from the low elevation to the high elevation reservoir. So the flow direction is that the pump will pump the water from reservoir A through pipe 1 to pipe 3 and to reservoir C. And for the reservoir B is similar, so we pump the water through the pipe 2 and to the pipe 3 and finally to the reservoir C. So essentially, we can consider these two pumps as a parallel pump to the pipe 3. So as we learned in previous problem, that if we have the pump in parallel, we can basically sum the pump characteristic together and to calculate the corresponding system flow rate. However, in this problem, we need to consider the friction head loads for the pipe 1 and pipe 2 before we can combine these two pumps together to calculate the flow rate at the pipe 3. Okay, so keep this thing in mind. Let's start the calculation. So here I collect the information for each pipeline and the reservoir data shown in this table, and the K here is equal to is equal to 0.0252 factor F times the length of the pipeline divided by the diameter of the pipe to the power of 5. This is for the English unit. Okay, so with the information that we provide here, we can calculate the factor K for each pipeline using the equation. No, not this one. Using the equation that I write on top of this page. Okay, so here are the basic information, and we have our friction head loads formulation, friction head loads equation shown here, which is K times Q to the power of 2. M is equal to 2 here. Okay, so what we need to do is that we want to calculate the net head that can be provided by each pump to this pipe 3. So what does that mean? So for example, we want to calculate the net head that can provide by the pump 1, that may give it's a star here, will equal to the pump 1 given the flow rate minus the friction head loads at the pump 1 given the flow rate, and minus the elevation difference between let me write in a notation here, between C and A, okay? And the net head that can provide by the pump 2 is equal to this. This is flow rate at the pump 1. This is 2 minus the delta H BA. Okay, so after we calculate this net head that can provide by pump 1 and pump 2, the friction head loads at the pipe 3 should equal to the energy that provided by pump 1 and pump 2. So we can plot the relationship. This is also the function of Q3. This is the function of Q3. No. This is function of Q1. This is the function of Q2. Okay, so we want to plot this relationship in a figure and to find out the intersection where the numbers satisfy this equation here. Okay, so keep this idea in mind. We need to first calculate the net energy provided by pump 1 and pump 2 using these two equations. So here's a table for the result. The pump 1, given the flow rate, we can know the pump 1 through these pump characteristics. So basically copy this column to here, and we want to calculate the net pump 1 using this equation. So we need to minus HF1 given the flow rate and minus the elevation difference between the reservoir C and reservoir A, which is 120 minus 100 feet. So that's equal to 20 feet. So, and we calculate these friction head loads using this equation here. So every number you know by the data that I provided at the left-hand side. Okay, so you know these friction head loads given the flow rate, and you know the elevation difference between the reservoir C and reservoir A, then you can calculate the net energy provided by the pump 1 to the pipe 3. So let's look at the first row. When the flow rate equal to 0, the friction head load at the pipe 1 is also equal to 0. So the net energy provided to the pipe 3 is equal to 200 minus 20 feet, which is equal to 180. So you can do the similar things for the rest of the rows and fill out these numbers by using this equation. And similarly, we can calculate the net energy provided by the pump 2 to the pipe 3. So we minus we calculate the net HP2 by minus the original HP2 with the friction halos at pipe 2 given the flow rate minus the elevation difference between reservoir C and reservoir B, which equal to 120 minus 80, which is 40 feet. Okay, so let's look at the first row. Because the flow rate is equal to 0, so the friction halos is also equal to 0. So we only need to minus the elevation difference, which is 40 feet. So 150 minus 40 is equal to 110. So you can use this formula with the friction halos equation shown here to calculate every number in this column. Okay, and for the last column here, we simply calculate the friction halos for the pipe 3. So we can plot the curve later. So that is easy, right? Because you can use the equation shown here, and you know the K value using the equation that I show on top of the page here. So you can plug in different flow rate number and fill out this column for the friction halos at the pipe 3. Okay, so now we have the information about the net energy of pump 1 and pump 2 that provide to the pipe 3 to balance the friction halos at the pipe 3. And the idea is to try to plot this figure. But the question that we want to ask is, how can we plot that figure? So instead of using flow rate, because different pipeline have different flow rate, so we cannot really, that is the thing that we want to find out. But to plot this figure, we want to change our common item here to the head. So here, instead of the flow rates, we change to the head. So given the interval to 20 feet, we can interpolate the net flow rate at the pump 1 given the head, and the net flow rates at pipe 2 given the flow rate. And then we can know the flow rate for the system, which is the flow rate at the pipe 3, because Q3 is equal to QP1 plus QP2. This is equal to the Q system. Okay. And to interpolate, for example, to interpolate the net QP1, we use this column and this column to interpolate the flow rates for to interpolate this. Okay, let me use the same notation here. And to calculate the second column here, which is the net flow rate for the pipe 2, we use sorry, mistake, it's this one. And for the pipe 2, we use this column and this column to do the interpolation. Okay, this is star and this is square. Okay, And you calculate the system flow rates by just summing out the first two columns. And for the flow rates at pipe 3, we use the last column in the previous table and the flow rates column to interpolate this column. Okay, let me stop here for 3 seconds so you can copy this table. And let me move down so you can copy this table again. Okay, so after you calculate the table here, we can plot those data into the Excel. And we get the figure that I show on the right hand side. The blue curve is the friction head load at the pipe 3, and this yellow color, yellow curve is the combined net pump curve, which is the plot using these two columns, and the blue plot is for the pump 1, so is these two columns, and the red curve is for the pump 2, which is these two columns. So how do we use this figure to find out the flow rate in each pipeline? As we said, we want to find the balance points that the energy provided by the pump 1 and pump 2 is equal to the friction head loads at the pipe 3, which is the intersection between this yellow curve and the blue curve. So from this intersection, we find out the flow rates at pipe 3 is equal to 34 CFAs. This is 34. And the corresponding head is okay, that's just using H as a notation. This is a total head we have is equal to the friction head loads under pipe 3 is equal to 90 feet. And to find out the flow rates as a pipe 1 and pipe 2, we will use this head that we found and the red curve and blue curve to find out the corresponding flow rate. So for the flow rate at the pipe 1, if we using the HP equal to 90, we can find out the intersection with this horizontal line and this blue curve to find out the corresponding flow rates for the pipe 1. That is equal to 22.5 CFAs. And similarly, we can find out the intersection with the red curve and this blue horizontal line to find out the flow rate for the pipe 2 that is equal to 11.5 CFAs. Okay, so now we have solved this problem with these 3 flow rates in pipe 1, pipe 2, and pipe 3.